everything around us is made up of trillions and trillions of protons and electrons. These particles have a common property called charge. So charge, what is it exactly? So there's a couple of characteristics. One of the characteristics is that property of charge determines how much something will interact with other particles that also have charge. So interacts with other charges, as we'll call them. So charges being other particles that also have charge. The other thing being that particles with charge will interact with or create electric fields that we'll talk about later. Interacts with or creates electric field. Okay. So how do we quantify charge exactly? So the standard unit of charge is called the coulomb. So coulomb. Okay. We abbreviate this with just the letter C. So C represents coulombs of charge. There is a common constant that we use a lot. We represent this with the letter E. So this is a numerical constant. E is sometimes called the elementary or electron charge. And the value of it is 1.602 times 10 to the minus 19th coulombs. So that's a given constant. And when we look at particularly protons and electrons, so let's say that we look inside these atoms. So we have the nucleus. And the nucleus is made up of tons and tons of protons potentially. Or if it's something like hydrogen, it's only one. But the number of protons determines what atom it is. So there's a nucleus. It's made up of protons and also another particle called the neutron, which has actually no charge. So the protons, okay, its charge is positive this number. So in other words, a charge of plus E. The neutron has zero charge, no charge. Outside the nucleus, we have electrons. So electrons somewhere out here. And we'll represent that with a minus as opposed to a plus. And that suggests that the electron has a negative charge, but it's actually the same amount of the elementary charge, but instead of positive, it's just negative, that amount. So it's minus E. Okay. So this is what we use. We'll focus on the protons and the electrons. So we notice that this is a really small number for the amount of charge in coulombs. So how much exactly is 1 coulomb of charge? If I were to have 1 coulomb of charge, is that a lot or is that a little? So, for example, we have 1 coulomb, and we want to know the number of protons or electrons that we're going to associate that with. So let's just say we find the number of electrons that's associated with 1 coulomb of charge. So this elementary or electron charge is essentially a conversion factor, because what it tells us is this amount of coulombs of charge equals exactly 1 electron charge or proton charge. So we use this as a conversion factor in this case So we want to cancel out the coulombs here, so we put coulombs on the bottom. And we write the number of coulombs, so it's 1.602. We use 1.6 a lot. We'll probably just round it to 1.6 in the future. Times 10 to the minus 19th coulombs. And that's equal to 1 electron of charge. So we write 1, and we can just abbreviate E for electron. So let's just say we calculate this out. So we have 1.602, 10 to the minus 19th, and it's on the bottom. Flip it up. That's going to be 6.24 times 10 to the 18th electrons. Okay. So we have that a trillion is on the order of 10 to the 12th, a billion's 10 to the 9th, and a million's 10 to the 6th. But this is well over a trillion electrons that are associated with 1 coulomb of charge. So that's a lot of charge. So what we're going to find is that when we have even 1 coulomb of charge, let alone more than that, 100 coulombs of charge, it's a significant amount. So let's take a look at some examples to really get a scale of exactly how much charge this is. So this first example, to have even 1 coulomb of charge is enormous because of the number of electrons involved. One extreme example of large amounts of charge occurring in nature is in thunderstorms, where there could be 20 coulombs in a typical California thunderstorm, maybe more in a Midwest thunderstorm where it's really, really powerful. Calculate the number of electrons that would correspond to this amount of charge. So very simply what we're going to do is we're going to take the 20 coulombs of charge and we're just going to convert it over. Okay. So essentially what we just did, we're going to do again. It's just going to be 20 times that amount. But what we would do is we'd say, okay, so for example, we have 20 coulombs of charge, convert it, 1.6, 10 to the minus 19th coulombs on bottom, cancel out the coulombs, and on the top we have that number corresponds to an electron. Do this, equals, so it's the previous answer times 20, and we find that this corresponds to 1.25 times 10 to the 20th electrons. Okay. So generally, when you have more than 1 coulomb of charge, maybe you have up to 100 coulombs of charge, you're talking about things like thunderstorms, which are enormous and very, very, very powerful and full of energy. So generally, we deal with charges that are a lot smaller than this quantity, just for us to be able to check our answers. So let's take a look at another example here. Charge in the nucleus. A common isotope that is found in radon, in which the nucleus consists of 86 protons and 136 neutrons. Calculate the total amount of charge in standard SI units, in other words, coulombs, in the nucleus. Okay, so we have, in this case, the number of protons and neutrons, and we just want to get the amount of coulombs of charge. Okay, so this is essentially the same thing, but we're just going the other way around now. Okay. So now we have our protons, which we know have charge, and we have neutrons, which have no charge. So what we're going to do is we're going to ignore the neutrons, and we're just going to take a look at the protons. So we have 86 protons. Now we know that protons and electrons have the same charge other than their sign. So we can practically ignore that, and we could still just call it an electron charge, E. We're going to set up the same conversion factor. Okay. So this time we need to write the number of particles, electrons or protons on bottom, E. And we're going to write the number of coulombs of charge on top that corresponds to that, this number, 1.6 times 10 to the minus 19th coulombs. Now, we calculate this out, and we say 86 times 1.6, 10 to the minus 19th. And we find that it's equal to 1.38 times 10 to the minus 17th. And because this cancels out, we just get coulombs on top, which is what we should be getting. So we get a charge amount which is pretty reasonable in terms of the scale of protons and electrons. It's 10 to the minus 17th, so it's a little bit bigger than 10 to the minus 19th, which makes sense because we have more than one charged particle. Well, let's take a look at one last example. Net charge of an atom. Consider that we have an atom of oxygen which is ionized, meaning that it has lost an electron. For oxygen, this would mean that it has 8 protons and 7 electrons. Normally that number would be balanced if it was neutral, 8 and 8. Calculate the total amount of charge, again in SI units, in the atom. So here we have two kinds of particles, both protons and electrons, that have charge. So there's a couple ways that we can approach this. We can either calculate the coulomb amount for both of them, so convert 8 protons to coulombs and convert 7 electrons to coulombs, and then put them together. Or we could realize that they have the same amount of charge, and we could add or subtract the two numbers, depending what they are. Now, because protons have a positive charge and electrons have a negative charge, we do have to account for that. Because if we had 8 protons and 8 electrons, then the net charge or the total charge would be 0, because we have plus and we have minus, so they cancel out. So generally, we need to subtract the numbers that we get. So the net charge overall, okay. Now, a lot of times we use a letter to denote the charge. We use the letter Q for it. So let's just say we call the charge Q. Okay. We're going to say that this charge is equal to the charge given by the protons. Let's call it Q plus. And then we have plus the charge of the electrons, call it Q minus. Now, we could say that for the charge of the protons, we have 8 times the value of E. Okay. And for the electrons, we know we have 7 of them in this case, so 7 times, but it's not E, it's negative E. Okay. Because we know that we have negative charges with that. So the charges will ultimately end up subtracting from each other. So we have 8E minus 7E, and that gives us just an overall charge of E. So in other words, the net charge of this system is just 1.6 times 10 to the minus 19th coulombs positive. So this indicates that we have one extra proton, or one electron that's gone. Okay. So this answer makes sense. So these examples give us a sense of the scale of charges. One last important thing to note is that this number you have to have in multiples. So what this means is that you can only have either 1 or 2 electrons, but not 1.5 of them. So you can have 1 of this number, or you can have 2 times that number, but not anything in between. This means that it's quantized. It comes in set amounts. So next we'll take a look at how these charges interact with other charges.